So are you ready?
Yes, TBC.
Something like this to tell you that there is 5 minutes remaining.
Yeah. I mean, just tell me whenever you want me to stop before people start throwing tomatoes and stuff, right?
Good morning. Welcome everyone to this Friday morning session of our workshop about physical application. Before we start, please check that your mobile is on airplane mode. So we will have 4 talks, and the coffee break just after the first one. And our first speaker today is Roberto Camassa, who will talk about internal wave propagation. So Roberto, it's your time.
All right. Thanks for, first of all, given that this is the last talk that I'm giving at this program, so thanks for the wonderful program for the organizers, and thanks for the invitation. And also thanks for your patience in waiting for a title, but the title I didn't change, Gennady. It's still TVC. Yeah, this is working collaboration over the years. Apologies actually to some of you who probably heard some of this material already. I presented here in Loughborough, or rather they are in Loughborough. And well, thanks of course to the support, general support actually by funding agents and Rothschild Foundation and of course the Isaac Newton Institute. Okay, so let me just give a brief outline. I'm going to work on or present examples on how these minimal models actually, I borrowed this terminology from, which I like very much, from Michael Berry's talk. I also don't like toy models. I like kind of cartoons maybe. But anyway, minimal models that can capture significant elements of the physics, aerodynamics, in this case, internal waves. And how minimal can you go is sort of the paradigm here before you actually have to give up something, especially the quantitative agreement. Okay, I don't have to actually dwell upon this because I guess it was already presented by Paul. I can add to this, so if you remember Paul's talk, let me use this data from the South China Sea shows an enormous internal wave, and I can add to what Paul already commented about. This dashed line is actually a model, a KdV model, fitted to match the amplitude, the eyeball norm amplitude of the wave, and you can see how the profile of the wave is not captured very, very carefully by the KdV model. And also I wanted to add, just to pay tribute to Leverstock and Stanton, who are probably the record holder in terms of big amplitude. Paul already commented about how you can achieve big amplitude because we really can do it without expending too much energy, given that density difference is minimal between top layer fluid or surface of the ocean type fluid. In this case, it's also the salinity is playing a role because this water here is not just warmer, but also fresher coming from the river, the Columbia River. And the ratio or say thickness of the top layer, if you can call it that way, and the amplitude is pretty ginormous here. So these are data collected, like I said, at Columbia River area. And so we set out a long time ago, about 15 or so years ago, in trying to get an experimental facility to actually do this in a lab. And we were fortunate enough to land a few grants from NSF and ONR and build this facility here, which is a wave tank. We custom designed it in such a way that we have a module tall and narrow, so you can actually study the deep water configuration, something that you've seen in the actual field experiments. A long section that you can actually shoot waves in a pretty much one-dimensional horizontal direction, and then a wide section that didn't fit in this slide, which is something like this, turned it on its side, so wide, and so you can study two-dimensional type wave patterns. And just to give you a sense of scale, this is the type of scale that we're looking at. So we're looking at 3 meters type total depth of the water. So it's a pretty good facility, and also, I should also mention, we have lifted it up from the ground and fit a glass bottom. So we can actually see things through the bottom and shine lasers, for instance, through the bottom, which means that you don't have to go through a disturbed interface at the top from the waves themselves. And you can study, this was actually designed, so this is the kind of schematic of that. It was designed to actually study internal waves mostly, but you can also do free surface waves. So just to give you a sense of what we're looking at when we do an experiment, this is an experiment done, actually, I should also mention, this facility is in collaboration with Marine Science, and we joined forces together to actually get this done. And these are Marine Science students who did this experiment schematically indicated here with the initial condition. So we have a top layer of fresh water dyed very, very hard, very, very blue. And in order to simulate, or emulate rather, a smooth transition between two fluids, the bottom is salty, and at this density, there is actually some dye in an intermediate layer, dye red, actually. So the camera is set close to the end of the tank. This is the gauge separating the deep section from the narrow section. And without further ado, I guess I'll just show you what the camera sees. So this is one of the panel, or the glass panes, rather, towards the end of the tank. And, well, these are internal waves, so they move very, very slowly. So you would have to be patient a little bit. But here it comes after you lift the gate, and after having traveled a long distance, comes a pretty ginormous wave, ginormous relative to the top layer. And also notice how just like in Magda's, I guess, presentation, how there is very little mixing of the red intermediate layer with the rest. So here comes another wave, and if I scroll, just to make it faster, comes another, and another, etc. Okay, so we did more quantitative experiments about 3 years ago using lasers to not just get the speed of the fluid under the waves, or in the waves rather, but also the density. Okay, there is a nice technique that allows you to back out the density from the fluorescence of a dye in the fluid. And so this is a couple of examples of two waves, one small amplitude, another large amplitude. This is the type of scales that we're looking at. A is an amplitude measured from the departure from the quiescent state, so this distance here, basically. And 1.54 for these numbers. You don't have to pay attention too much to these numbers, but it was mentioned already in the talk by Paul and others that there is a maximum amplitude, there is a flat top type wave or conjugate state, and this is very close to that limit already. The color scheme here is completely accidental. There's no reference to geopolitical events. or for that matter, to an event that is going to take place this afternoon, I believe. But nonetheless, I figured, you know, I would mention this because although the colors are inverted, I mean, this is an important event. So for those of you who have skin in the game, so to speak. Yeah, so going to the modeling, there is a natural model for this situation, which is the Euler equations, in which you neglect viscosity. Viscosity doesn't have really time to act too much. Also, you neglect diffusion of salt in this advection of density equation, simply because, again, there is no time for diffusion to act. And you've seen in the experiment in the movie that that's pretty much the case. So, okay, rigid plate on top. Well, that's not really happening in our experiment, but if I play the movie again, you will see that the displacement of the free surface is really not there much. Okay, you would have to really go into the millimeter scale to see something for the parameters that we have, of course. Okay, so with that, you can what can you do with this? Well, not much by pen and paper or pencil and paper, but certainly you can throw a computer at it. And so this is a direct numerical simulation of the Euler equation that we did. And we used a code, or rather, we helped develop a code that is now called Verdun, and or its most recent incarnation, which we put to lots of tests, and we sort of trust. So this is the schematic. This is in agreement with the schematic that I showed for the tank. The actual scale is this. The experiment that you've seen is lifting a gate, and this is what you could have seen if you were to take a bird's eye view of the whole thing. Okay, so it's clearly it's clear now that what you see from the side view of the camera is really waves belonging to a dispersive shock. Not surprisingly, perhaps, given that you're looking at a dam break, so a Riemann-type problem in a dispersive system, as we heard a lot, actually, during this workshop as well as the program. So the actual scale is actually much more elongated, of course. We're talking about 27 meters. Okay. Yep. 2D simulation or 3D? Ah, very good. This is 2D. 2D. Yeah. Yeah, so there are 3D effects when you lift the gate in the wake that you possibly are referring to, because there is a lot of turbulence, right? Yeah. Yes, yes. I mean, as far as, well, again, the proof is in the pudding. Once you look at the experiment, right, you don't see much in the transverse direction. Yeah, thanks, yeah. So, so there are actually, so that's not very quantitative, but there are careful experiments by Grew and et al. So we set up with their numbers, with their parameters, physical parameters, to reproduce that experiment in silico. Okay, so, oops. So this is what happens when you lift their gate, in principle. So they had wave gauges at these locations. You can see that there is a pretty large wave for that setup that develops. And you wonder if that wave is a solitary wave. So in order to do that, well, first of all, I should say that we used the smoothing of the transition between the two densities by hyperbolic tangent. These are the parameters. We try to match with this number the thickness that they report in their experiment between the two layers. And then we just set up our software probes, and you can see that the first probe, of course, gets the wave first, and it's this amplitude, and it develops into a smaller amplitude wave. So it's still evolving, presumably, to getting to be a solitary wave. What you saw at the beginning wasn't quite developed. because the decay in amplitude that you see cannot be due to viscosity alone. Of course, there is a small decay all along because of viscosity, but it's negligible on these distances. Okay, so another test for the code is to, okay, we can compute traveling wave solutions because they are stationary solutions in the right frame of reference. Independently, we use this code by Turkington and collaborators, which is also coming with a theorem of convergence. Okay, so we know that this code is going to converge to the exact solution. The exact solution is called the DJ of what? The DJL equation, as they are called once you look at the traveling wave solutions. And so you fix parameters, and you get the wave profile. You stick it into the time advancing code, Vardan, for evolution, and check that it travels. And it does, sort of. It's got a little wiggly tail, which has to do with something that we're going to talk about. But mostly, it travels at the right speed, maintaining its shape. Sorry. But if you use so a caveat, okay, if you use the TW code, the stopping criterion for the iteration to be called it converged was when you, between two successive steps, in some norm you get 10 to the minus 5 as an arbitrary threshold. But that's dangerous because it's only an assessment of how, if you think about it, how slow your code is actually converging, right? It doesn't have to be very close to the actual solution. And you can see it, even though to the naked eye, you couldn't see any difference between the two initial conditions. If we stopped at this criterion, it definitely falls apart. And you can monitor potential energy and other monitoring quantities, and you can see that it doesn't really work. Okay. So I mentioned potential energy, but there is also a nice structure, which is it's a Hamiltonian structure. So the total energy, if you will, is much more than just an energy. Is actually there is a Hamiltonian version of the equations of evolution that is due to Benjamin. I like this structure as opposed to others that have been proposed in the literature because actually the quantities that are being advanced in or constitute the Hamiltonian pair are measurable quantity. So this is some sort of weighted vorticity by density and the density itself. And they're both measurable. They don't involve a potential or Clebsch potentials in some other versions. I should also mention that if you consider the fluid as stratified continuously, there is no conservation of vorticity. Okay, so you cannot really use potentials all that willy-nilly. Okay, yes, please. The question is whether this is the full-blown absolutely. Yeah, so this intermediate step, okay, for this, so you have to solve an elliptic problem in order to eliminate this quantity here, the stream function. That's no surprise. I mean, pressure has to be eliminated from the equations, right? So there's always an elliptic step involved. But yeah, it's fully nonlinear. I mean, it's the whole thing, actually, the Euler equations that I showed you before. Oh, 2D. That's important, okay? The 3D version of this is actually something of interest, but I'm not going to talk about it right now. Anyway, so simplifications. Okay, so you have this Hamiltonian structure, but still cannot do much with it. But you can now try to simplify life a little bit by saying, oh, let me assume that my transition of densities happens on a surface, okay, and consider two densities. Okay, now you can possibly impose irrotationality in both layers. We don't do that per se. The price you have to pay is you have two Euler equations that you have to match across an interface according to the pressure continuity. Okay, can you do something with it? Well, the numerics gets greatly simplified now because you work on a surface. And this work by Grew did exactly that. did experiments, first of all, like I mentioned, and also did computation of traveling wave solutions for the two-layer situation. And again, you have to use a computer. The matching with the data and solid line is the Euler is pretty satisfactory. But also KDV, which is this dashed line, is not too shabby either. On the other hand, if you increase the amplitude, and you can in this situation of internal waves, then KDV, just like we saw in the very beginning, right, falls way behind, and Euler keeps going pretty much on top of the data. Okay, so with that, you say, okay, now I still want to do something with pen and paper, and can you do something with Euler two layers? No, the answer is still you need a computer. So develop models. One possibility, given that you have such a large amplitude, is to do asymptotics based on the only small parameter that you have is just the fact that the steepness of the wave is very, very small. Okay, so small steepness means essentially the length scales or horizontal displacements are much larger than the vertical scale. So you have a natural small parameter in the problem that you can exploit. And out comes this model written here in all full glory, but the details don't quite really matter. The only thing that I wanted to point out here for the actual formulae is the fact that this term here is formally of lower order than this chunk. Okay, this is for the top layer. There's a similar equation for the lower layer. Actually, Paul already mentioned this set of equations as being doing a good job. This is really the key operator for dispersion, and it's nonlinear. Okay, so it involves nonlinear terms, not just because of this term, but also in the velocity. These are horizontal velocities, layer average. So still the advantage of this model is the fact that you completely get rid of the vertical velocity. You don't have to solve for it anymore. The Hamiltonian structure that I mentioned before, well, there is no direct connection between these equations, which were obtained at the level of equations, not Hamiltonian structures, and the Hamiltonian of Benjamin that I showed before. Recently, with my student, in fact, it is his work, Russ Arnold, who was here, we actually wrote down the Hamiltonian for this system. Otherwise, you can live with a coupled 4 equations and write down a mixed type Lagrangian Hamiltonian called Ralphian. Anyway, so these are all interesting structures, but at least now with this model, you can actually find closed form solution for solitary waves. Okay, closed form, explicit as in tabulated functions, elliptic functions. Again, details don't matter. I mean, the match with Euler versus model is exhibited here for 4 amplitudes, going to large amplitudes. And okay, we can have to really, at least on the graphic accuracy, you have to squint to see the difference between the two. So the dash, long dash is the model, and the continuous is the Euler solution that we saw before. Okay, so compared to experiments now by Grue, again, not surprisingly, the wave profiles match pretty well. Not just the wave profiles, actually. So there is an effective wavelength integrated area, essentially, of the wave versus the amplitude type pattern that is reproduced by this curve, by the model, and the data are pretty much on top of it. Likewise, this nonlinear dispersion relation, there's a formula for this written here, versus amplitude. Okay, and the speed of these waves changes with amplitude and goes to a limit in the conjugate state that Paul talked about yesterday. So all of this is pretty much satisfactory. There is also fluid match, okay, fluid quantities match. So horizontal velocity, for instance, is also matched pretty well by formula, thanks to the model. Okay, so here you have two different amplitude waves. We took a cross-section right across the peak of the wave, and we look at they looked at the horizontal velocity. There is a jump almost a jump in velocity, because if you think about it, right, if you are in a frame of reference going with the wave, okay, so the water is coming at you, okay, the wave is a wave of depression, so it pushes water down, or the interface down, so you have to squeeze through a neck, and you have to speed up to conserve volume, whereas in the trough above, you have to fill up a belly, and so you slow down. So there is a jump in velocity between top and bottom across the interface, okay? So there is a shear, and the shear is matched pretty well. The experiment by Grew were with a very small transition between the two layers. It's not perfect, and also you can see that there is somewhat a slope here, okay, in the transition between the two velocities. So that more about that later. Okay, so quantitative agreement. So we got a simple model. This is, I don't know if it really said that, but it's quoted everywhere on Google anyway. And so I think, anyways, it's fitting, okay? So you should make things simple, but not too simple. And it turns out that it actually is too simple in this case to get a quantitative agreement. So you have to work a little harder, and the little harder is about accommodating this smooth transition between the two layers. Okay? So it turns out that this makes a difference, unexpectedly large difference. And we were, with Roxana Tiron, some time ago, we were able to actually get some systematic way of introducing this, accounting for this transition, for the smoothing due to diffusion between the two layers. These are miscible fluids, okay? So there is no, I should have mentioned that, there is no surface tension separating the two fluids. Okay, so how do you do that before? I mean, it's not a fitting. You could also fit an experiment, but you have to do it a priori so that from then on you have the model, okay? And it's about choosing which density you want to use, okay? Yes, you're going to pretty much constant density in the top layer and bottom layer in the experiment, but where do you put the transition for the two layer? Two layer has to be, you know, you have to have an H1 and H2 depths, right? So where do you put it? The simple-minded thing is to just put it at the intermediate, the mean density isoline, and that you call H1 or H2, or rather Z0, like I mentioned here, right? You put it right there in the middle. But that may not be the most intelligent choice. Okay, so the possibly good choice is to try to match things like mass in the water column, potential energy in the water column. You don't have velocity yet. And possibly try to also, you do have speed of linear speed of mode 1 waves, and you might want to match that. So if you try to do this, how comes a choice for H1, H2, rho 1, rho 2, that when you compare with the direct numerical simulation, you actually match pretty well. So this is the dispersion, nonlinear dispersion relation, velocity of the solitary wave versus amplitude. This is the curve that you get from the two-layer model fitted, not fitted as in fitting an experiment, but rather intelligent choice or optimal choice of the two layers. And this would be the mean value type choice, okay? So there is a pretty sizable discrepancy between the two. For this fairly possibly big, maybe diffused interface, okay? 4 centimeters, or this number, non-dimensional number, 0.26. For Grew, just to give you a perspective, Grew had the half of this, okay? So much thinner. And of course, there is a theorem that says if you go in the limit of 0 thickness, you converge to the two-layer case. The theorem by James of some times ago. So these curves will migrate to this eventually, but not quite. And we were surprised to see that big of a difference, but we knew there was a difference because because of the simulation that we were doing, essentially. So you can actually go to pretty ginormous diffuse density in this case, and still get good agreement with the optimal two-layer versus the actual direct numerical simulations. Of course, it's not perfect, but now you can see this slope of the velocity field. What I'm plotting here is velocity, horizontal velocity versus depth across the interface. Okay, so there is a definite slope that you might want to capture in order to get quantitative agreement. Okay, so with that, you now can put the model to work to get time-dependent simulations. Okay, because so far the model was only good, to some extent, for traveling wave solutions in pen and paper type sense. Okay, you still need a computer. Okay, so you start trying to account for the wall at the end of the tank by just reflection. Okay, so you have to pay a price for your simulations, but eventually you get to do this type of simulations with the interface here highlighted in, well, I don't know what color this is, actually brown now. It should be reddish. For two different experiments, for this type of density stratification, because of this density stratification, we cannot really start very sharp here. We have to smooth out the step a little bit. And for the large amplitude, you can see the same thing that we saw with the previous movie reproducing Greu's experiment. And okay, so if you pick this isoline according to the optimal choice for the direct numerical simulation, I compare with the model. So red is this isoline here, and the model evolution. So it takes hours for the full Euler, the direct numerical simulation, minutes for the model. Still, you need a computer, like I said, but it's pretty satisfactory. The main wave is captured pretty well, both in amplitude and in location. Okay, there are actually two curves here, the solid and the dash. There's two variants of the model, which I don't have to dwell upon. Okay, so problem is, you still need a computer to make any prediction. So if I give you a gate, a certain distance from the end wall, and a certain depth behind the gate, can you predict the amplitude of the wave that comes out, the first wave, okay? And can you predict whether you have 1 or 2 or 3? Now, this, I have to, of course, pay tribute to Gennady, because he gave us, in his first talk of this workshop, a way to address this, possibly. I haven't tried it yet. I know I have to try it. Okay. But one possibility is to also take an alternative approach and try to derive from the Hamiltonian structure something which is completely integrable, so you can actually make prediction from the get-go. Okay, so that's what we try to do. The details are cumbersome. We have a paper submitted actually about this. So I won't dwell upon this. It's just a sequence of steps which are well codified in order to derive a model from a Hamiltonian, which has to do with Dirac brackets and all that. So let me just skip on this. Just mention that at the end of the day, you still have to do some asymptotics. And the asymptotics is again the one that I showed you before. But now, unfortunately, I need some small amplitude assumption in order to get to a completely integrable model, a model that I can actually do more with. Okay, and this scaling is the one that I like. So the epsilon is, think of it as a scaling for dispersion, and alpha is scaling for amplitude. And amplitude is intermediate between these two small parameters, dispersion so there is a relative ordering of small parameters. So the asymptotics has to be carried out with two small parameters, okay? And of course, you have to say something about the relative ordering, and which is this one. So if you do this, you get to this model in which you're allowed to retain this alpha squared small parameter, which is subdominant with respect to alpha, okay, simply because you say, oh, everything else that I drop out is high order with respect to this fellow here. Okay, so it would be epsilon alpha squared, for instance, is already neglected. And okay, all the physics is encoded in these coefficients. Once you non-dimensionalize, this is nothing but you recognize the linear wave speed. And the most important parameter here possibly is this b, which changes sign exactly when the wave turns from depression to elevation. Okay, so this magic ratio here is always there in this business, and it's a ratio of undisturbed layer thicknesses versus densities. Okay, so you could drop this term formally, yeah, and possibly don't pay much of a price, but it becomes relevant for sure when now b, this parameter that can vanish, vanishes. Okay, so for those of you who are familiar with this, is modified KdV type behavior or Gardner equation type behavior. So if you're close to this magic ratio, when b is very, very small, presumably the model should be requiring this term and do very well, and it does. Okay, so here there are two curves actually superimposed to each other. Okay, so and this is the KdV curve again for the nonlinear dispersion relation, velocity versus amplitude. Okay, so the model is pretty good in this situation with this term retained, but surprisingly, at least to me anyway, is that actually even when in principle you could drop this term for the GRU again experiment type parameter, it is actually necessary to get a good agreement with, okay, I should have mentioned this. The black is the two-layer model, okay, the formula that I showed before, okay, and this is the approximation that I got from the Hamiltonian. So it still does a decent job, at least for this quantifier. Okay, but what if you were to drop it nonetheless? Okay, if you drop it, then you get to this equation, which is actually known in the literature as the Kaub was the first one probably to actually analyze it, Kaub-Bouzinès to distinguish from other things, okay, and which is completely integrable now. Okay, so there is a lax pair, there is an isospectral problem, you can actually get the dam break. The dam break is the easiest of the spectral problem to solve, and you can actually do well with that, yes. You can compute solitary waves contained in this initial potential well by solving the spectral problem. And unfortunately, is good for nothing in terms of evolution per se, okay? Because it's severely ill-posed, and ill-posed in a way that is actually a kiss of death, essentially, because it does not depend, is baked in the coefficients, physical coefficients. It does not depend on the amount of jump that you have between the two velocities, which would be already Euler. You know that there is a shear instability associated with that. And okay, then it's really not worth trying to simulate numerically to follow the evolution. But you can predict the number of solitary waves that eventually will, according to inverse scattering, will eventually emerge from an initial data like a potential well, a square. Okay, so you could do something to rescue both the Kaub-Bouzinès and in some sense the integrability by being close to it. Okay, so this is a model that we propose, and it's equivalent to the going from KdV to the Benjamin-Bonham-Mahoney equation. Okay, this, on the other hand, is known for a while. We really didn't do too much with it until now, essentially. And okay, so do the models work? So again, the gold standard here, to some extent, is the two-layer model or the direct numerical simulations. And for weak nonlinearity, the dam break problem evolution that I showed before, okay, so in green, you have the, let's see, the strongly nonlinear model, so the two-layer model that I showed before. In black, the direct numerical simulation of Euler. And here you have the evolution of either of those two models that I showed before. So the amplitude for the weak nonlinearity is OK for the BBM-like model of Kaup, not so much for the phase, right? There is a clearly speedier evolution for the recursive wave. Also, it predicts an extra solitary wave, which is actually what the Kaup model also predicts. I don't know the phase for the Kaup prediction, okay, because I don't have the evolution. I would have to solve the whole inverse scattering procedure, but I do know what amplitude eventually they will reach, the asymptotic amplitude of the solitary waves. And there are two, as opposed to possibly just one for the DNS and the strong nonlinear model. If you go to higher nonlinearity, not surprisingly, you're missing more, in a sense that you're predicting more waves. But the amplitude actually is not so bad, actually. Yeah, at least for the Kaup-Boussinesq version. OK, so in the remaining 10 minutes or so, I want to switch gears and go to another, again, put the model to work, OK? And what we have with this Optima model is a minimal way of getting the two-layer adjusted to an interface, okay, diffuse interface. With that, you can possibly address this instability that I kind of alluded to and you already seen in the simulation, the shear instability and the roll-up a la Kelvin-Helmholtz, for those of you in the know. Okay, so this optimal two-layer model allows you to fit a linear velocity profile transition. So now velocity profile is continuous. And the density also continues. And the relation between the two, density is quadratic if the velocity is linear. This is actually a property that is maintained throughout this modeling. OK. So with the linear velocity profile, and so knowledge of the density and velocity profile in the interface, what you can appeal to is that the waves are very, very gentle. Okay? So you can locally think of the linear velocity profile and the density profile quadratic as parallel shears, respectively, right, and transition of density. So for this situation, the stability analysis boils down to what's called the Taylor-Goldstein problem, in which you have to solve a Sturm-Liouville type problem with C now, the phase speed, omega over k, as your eigenvalue. If you fix k, k is the wave number. So for any wave number that you give me, because of this decoupling of the linear problem or separation of variables, okay, you fix k and you find C, solution of this problem with these boundary conditions. Okay, so this is a well-known thing, many works on it, and okay, so if you get a C which is complex, that means that omega is going to be, well, there is a complex number here, and you can get growth or decay. Okay, so the fundamental theorem in this business is the theorem of Lou Howard, that pointed out that this non-dimensional number, it's a ratio, if you will, of shears in density and velocity. Okay, if you have this number, the Richardson number, less than a quarter, then you have the possibility of an imaginary component of your eigenvalue, which means instability. Okay, it's a possibility. It's not. So the theorem should be read backward. Okay, if you're above 1/4, you're always stable. Okay? If you fail to be above 1/4, you may be unstable. Okay, so direct numerical simulations of a traveling wave, you can actually compute the whole region around, along the wave profile in which this Richardson number is less than 1/4. So this pocket here that opens up below 1/4 is where you have the possibility of instability. This instability for the parallel shear would be Kelvin-Helmholtz, saturated to Kelvin-Helmholtz instability. Okay, so you have to choose a very narrow transition between the two densities in order to be below 1/4, simply because this sits at the numerator, so the smaller this is, the better. And okay, so it's not really well said. Anyway, if you're narrower, you have a jump in velocities occurring on a sharper transition. And let's see, I think I should say that the denominator wins. Okay, the denominator is du di square. I should really say that. So okay, so you can do a study of how this pocket changes in terms of different amplitudes. So the first opening of the pocket is at a small amplitude, and as you increase the amplitude for everything else fixed, this parameter of thickness, actually, of the transition between the two densities is fixed. And then this pocket becomes larger and larger. So all around here, you have the possibility of instability or shear instability. Can the model do anything like that? The answer is yes, actually, almost anyway. So the length of the pocket as the amplitude increases can be predicted by a formula. The Richardson number can be predicted by a formula. And this magic line in which it seems like the pocket terminates at depth is also being predicted by a formula, thanks to the model. Okay, so can you be quantitative? Yes, actually. So if you look at the spectrum for two different waves, okay, so this is a stable wave, and the spectrum of just fix a k and get the c's, well, there is no imaginary part. You are stable, and these are the crosses are the model, and the x's are the direct numerical simulation, so not too shabby. And also you can predict the imaginary component of c, which is your growth rate, okay, in time, also satisfactorily close. You can do more because now you have a profile of velocity and density, so you can solve all along the wave profile your eigenvalue problem, the Taylor-Golding. And you can see that there is an interesting situation in which so out very far away from the wave, there is no motion. So these are the classic baroclinic modes of oscillations for linear waves for a continuously stratified fluid. So you have an infinite number of eigenvalues accumulating onto 0. You follow a few of them as you move towards the center of the wave when the shear develops. And you can see that all these modes kind of accumulate on the extrema of the velocity jump. Okay, there is a maximum velocity jump between the lower and top layer, and they come in, accumulate, collapse from above and below to the extrema of the interval. And when your Richardson number is below 1/4, you may have an eigenvalue developing which has an imaginary component, and this is exactly where it pops up. Okay, so it has to come in, according to the Miles and Howard theorem, in the inside of this velocity jump. Okay, it has to be in there, according to the semicircle. There are interesting features of this eigenvalue problem, which I won't be able to go into, but it's not a symmetric operator, which means that your modes, your eigenfunctions, are not normal to each other. And this non-normal situation can lead to growth. I guess people have looked at it extensively in just general mathematical context. So I want to conclude with some examples which are amusing, I think. So you have a possibility of an instability. How do you trigger this instability? Okay, if you have a very good code, like we saw before, somewhat good, the instability doesn't really get to be excited by numerical noise until late in the game. Okay, numerical noise eventually will trigger an instability, presumably. But you can also zap the wave with a mode and then excite the instability to grow much more rapidly. And so that's what we did here, but in a way that is more natural, perhaps, to the environment. Okay, so if you're in the frame of reference of a large internal wave moving, and you encounter a patch of, say, mode 1 waves, linear waves, tuned in a way that the wave number is trying to trigger the instability that you would have in the trough. Okay, so you should see this instability grow. So this is such an experiment. So because the way the mode 1 waves, they're moving left or right, but they're slower than the solitary wave. So if you put yourself in the frame of reference of the solitary wave, you will eventually catch up with these waves. Okay, so they are moving inside the pocket of instability. So this is a stable shear situation, and you can see what happens from the different times here. Okay, so the waves are excited with some amplitude. The linear waves are excited with some amplitude and some frequency or some wave number. They get into the pocket and they emerge stretched in the wake, stretched because of this non-normal behavior, and somewhat a lower amplitude. And this is a stable wave, so there is no growth inside. There is no instability triggered. So you take a bigger wave or a thinner interface, and now you have a pocket of instability here predicted by the model as well as direct numerical simulation. I should say these are direct numerical simulations. Okay, so the wave is tuned to excite the instability in here, and it doesn't. Okay? So why? I mean, it behaves like there was no instability, even though it's tuned to do it. Okay, so this is, let's see, this is a right to left moving patch. So it's moving fast through the pocket. Okay, so if you take the counterpart, I said there is left to right or right to left. So take a right to left now, moving, the same thing, and now you see the intensification due to instability. So you might think, oh, okay, I understand what's going on now. Because it's moving in the same direction of the wave, it stays inside the pocket longer, yeah, roughly speaking. So it has more time to develop a growth of instability. But it's not that simple, actually. It turns out that it's not the case, actually. That's not the main reason, or probably the only reason for this. So I have to finish, so I'll just give a hint about what's going on, which took us a while to figure out, but probably because we were slow. But anyway, the thing that you should be thinking in this situation is a slowly changing in space medium. Okay, so your wave packet is moving into a medium which is slowly changing in space, but not in time, because you're in the frame of reference of this wave, it doesn't move, okay? So by the way, this is outline of the wave in terms of two isolines, just to show how thin it is and where the wave is, but otherwise green is zero velocity because we subtract off that velocity of the wave. So slowly varying in space, but not in time, medium, means that the frequency satisfies in a easily done modulating wave calculation, the frequency is fixed. The wave number is changing in time and space, because there is conservation of frequency. So what you should do instead is tune this fellow here in such a way that you, at some frequency, in such a way that once you get in here, you get the right wave number to excite the instability, okay? Because the wave number is changing all along as it moves into the pocket. Okay, so we did that, and this is really what this was mostly all about. So conclusions, I guess I just presented, kind of preaching to the choir, perhaps, after the talk by Paul and other people. But these models can be used to both illustrate qualitative effects well, give you intuition of what's going on, but also quantitative agreement if you again, you're simple but not too simple. And so these are the kind of the backbone for these studies. And yeah, so there's plenty of work to do still in many directions. One I just mentioned. I should have also mentioned Karima's point, which, sorry, Karima, I didn't have time to work on it. But you can turn this lower order model to do something that higher order models would do by using this normal form type idea that I guess Yuji Kodama kind of proposed. So, okay, thank you for your attention.
Thank you. You have time for a few questions?
Yes.
Thank you for a nice talk, Robert. I have a question about one of the graphs you showed where the phase was shifted, and I might have missed it. So is it due to the numerical diffusion you have? Yeah.
This one?
Yeah, because the amplitude is not as right, and the amplitude affects the speed. So is it numerical diffusion or it's a model artifact? This is what I missed.
I think it's a model, quite frankly. I don't think it's numerical. But honestly, I mean, we ran convergence tests, right? So changing the poor man's convergence tests, right? By changing the grid, right? And see that it is consistent. So I think it really is the model that is not doing a great job for the phase, and for the existence of fake ghosts, solitary waves. So actually, Gennadi's idea of doing the dispersive shock type calculation, I mean, this is a situation in which you only have one big wave, okay? So you're pushing your luck there, I think. But nonetheless, it's definitely worth trying to do that, yeah. It may do better in this, and then you don't have to do modeling, bend over backward to fit BBM type tricks and so on and so forth. So that may be good. So you just stay with your two-layer models and that's it, even though it's non-integrable.
Any other question? So if no, let's thank our speaker again.
Right. Thank you. So now, yes.
We had a chat with him, and he showed a very interesting kind of simpler model.
Yes.
Yes. So you
yes.
didn't show
Which one?